Hello, this is Ryan Woodward recording for Intel's Digital Logic course. This is Lab 2, Part 4. And in this part, we needed to build a way to show the sum of two 4-bit numbers, similar to how we did in Part 3 with the ripple carry adder, but we needed to extend that so that we could show a 5-bit number on the 7-segment display. Essentially, with switches, we pass in two 4-bit numbers via 8 switches, and then we use that through, I just implemented a binary coded decimal decoder, and that way it was easy for me to just go from inputting the 4-bit numbers and then passing that to the decoder. So part of it was that we only needed to show, or support rather, the sum up to 19, and that's partly because each of the 7-segment displays can handle 9, and with a carryout that is 8 plus 8 to 9 to 1, that makes it 19. But nonetheless, this circuit only supports up to the addition of 19. Otherwise, it will show two little hashes, or two little dashes rather, on the 7-segment displays. But let's get into the code. So similar to the previous lab, the previous part, we have the full adder and the ripple carry adder. And these are the very same circuits from previous. They are not different at all. However, I did include a very extended BCD decoder, and this was just to replace all of the circuits that I did in part 2. I didn't feel like adding them in. This was a much simpler way to do this, in my opinion, and it's a lot more straightforward. But basically, we have a 7-segment decoder, we have two 7-segment displays declared, and the input is 5 bits. And depending on that is what we see on the output. It's just a lot of case statements. It's a little tedious, but at the same time, it's very easy to get things off the ground, and that's why I did that. So for the actual Part 4 code, this is the circuit itself here in this Lab 2 Part 4. We have two 4-bit inputs, X and Y, a single bit input for the carry-in, and two hex displays as our output. This structural model contains just a component reference to the ripple carry adder and a BCD 7-segment decoder, that lengthy one I just showed you. And all we do is we pass in, we call that's not the word, but we create an instance of the ripple carry adder. We pass in X and Y and the carry-in to be added. And then the sum, these intermediate signals here, sum 0, which is a 4-bit number, and carry out, a single-bit number, will be the output. And what made this so easy was concatenation. So all we do is add this concatenate C out to sum 1. So basically, if C out is 0, and that will be if the parallel adder handles all the values. So it handles up to 4-bit numbers, so value of 15. And if it's greater than that, then we have a carryout. And that means that basically if we were adding, so it's like add 4-bit numbers, and if we go over that 1, that would be the carryout, shifts to that next bit position, so our 5th bit. And that just tells us that, hey, it might be even easy to look at here. So once we go over here, so we have, we'll go down to 15. Once we add one more, this bit will now be populated. And that will stay consistent for all the values that we need for this circuit. And so all we have to do is keep that 1, which is the carryout, and we'll concatenate the sum to that. And so if we were to say the sum is 15, we'll see that 1 concatenate the other extra 4 ones on the end, and that will be our 5-bit number that we pass into the BCD to 7-segment decoder, which is what we do here with this ampersand. And then the hex displays are passed in, or well, they're actually passed in, but they will be written to. And that's it. It's that simple. And that's it for the VHDL. And here is the Verilog version. I didn't bother to recreate or reshow all the code from Part 3 or Part 2 in the Verilog. Actually, I did not do the Part 2 in Verilog, but it took me a long time to get that one to actually work. But regardless, this is the same process. We have the concatenation occur here, and that's it. And here is a demo of. All right, and this is Lab 2, Part 3.
In this circuit, we have this input A, these first 4 switches, then input B, the second 4 switches, and we can display up to the value 19, as in the document that's what it told me to support up to, and that's the greatest 5-bit number I'm going to go to, but we'll see this second 7-segment display light up as we actually add to values greater than 9. Up until that, we'll just see this 7-segment display stay high, and as by default, anything lower than 10, I just want this one to be high. And if we go above 19, we'll see 2 dashes just to let us know, hey, we're above 19. All right, let's start by adding just 0, and we'll just increment 1, or A, excuse me, so that we can see this count up nicely. So we'll do 1, 2, 3, then 4, 5, 6, 7. Drop those back down to get 8, 9, and here we go, 10, 11, 12, 13, 14, and 15. Okay, so this is the max 4-bit number we can do. And so now by adding in B, we can start getting 5-bit numbers. So let's just add 1 to get 16, 2 to get 17, 3 to get 18, and then we will add 4 to get 19. And we'll just increment by 1 to show that going above 19 produces these two dashes here to show that we can't go above 19. But there we go. We are successfully adding 2 4-bit numbers with a sum to become a 5-bit number, and that's it. Thank you.